Hi everyone, here is our math problem for today. This is about solving equations with complex numbers. C to the third is equal to 2 plus 2i. Find the value of z. Now, what does this equation mean? This means that we are looking for a complex number z such that when you raise it to the third power, that is equal to the complex number 2 plus 2i. Now, let's solve this problem together. Let's begin by recalling our complex plane. In the complex coordinate system, we define a point z to be equal to a plus ib, where a is the real number part of this complex number and the b is the imaginary part. So if this is a and that is b, then this point is z equals a plus ib. The horizontal axis is the real part and the vertical axis is the imaginary axis. Now, if you have a vector coming from the point of origin going to this point, then the magnitude of this vector is the absolute value of z. Now, if you look at this vector in the polar coordinate system, it will look like this. We need an angle here, and let's label that angle as phi, and that radius is equivalent to the absolute value of z, which is equal to r. Now, this point was z equals a plus bi in the complex plane, but in the polar plane, we now describe this point as z equals r times the quantity cosine of this angle plus I sine of this angle. Notice that if I create a right triangle here, then the value of this r can be computed using the Pythagorean formula r equals the square root of a squared plus b squared. Now, we need to remember all these formulas because we are going to use them later on. Now, according to the Euler formula, this part here, the cosine of phi plus I sine of phi, that is equivalent to e raised to I pi. This is now the exponential form of the complex number z. And we are going to use this exponential form of the complex number in order to solve our problem. So again, our focus here is to find a complex number z such that when you raise it to the third power, the result is this 2 plus 2i. Now from here, we can compute for the radius. Because our a is 2 and our b is 2, then the radius therefore is equal to the square root of 2 squared plus 2 squared, which is equal to the square root of 8. That is now our value of r. Then we need also to know what is the value of this angle phi. But let us recall that we have here an isosceles right triangle. The length of this base is 2 units and the length of the height is also 2 units. And so, for an isosceles right triangle, this angle phi here must be 45 degrees or pi over 4. So we now know what is the angle, we now know what is the radius, then we can now represent our complex number z to be equal to r e raised to I pi, where r is equal to the square root of 8, which is this radius, copy the e, copy the I, and the angle phi is this pi over 4. This is in the exponential form of the complex number z. Now, notice that if I have this polar coordinate system, this point, which has a radius of square root of 8 and an angle of pi over 4, can also be arrived at if I rotate around the circle an additional of 360 degrees or 2 pi, and if I keep rotating around the circle for an additional of 2 pi. So there could be an infinite number of solutions to this equation. One of them could be z cubed equals the square root of 8ei pi over 4 plus 2 pi. That means I add 2 pi or 360 degrees to this pi over 4 to arrive at the same point. Or if I have a number k, such that k is equal to 0, 1, 2, 3, and so on, then I can write the general form of the equation this way. Z cubed is equal to the square root of 8e raised to I times pi over 4 plus 2 pi times k. In other words, I am going to add multiples of 2 pi in order to arrive at the same point when I rotate around the circle. Now, our problem is we are looking for z such that when you raise it to the third power, the result is this right side. Since this is exponent 3, we can eliminate the exponent 3 by raising both sides of this equation to exponent 1/3. So let's do that. If we raise this to 1/3, that becomes z only, then we raise the right side into 1/3, but this k must be defined to be k equals 0, 1, 2, 3, and so on. And therefore, the solution that we arrive at here would depend on what is that particular value for k. Now, simplifying this is a product that is raised to an exponent. So the first factor raised to exponent to 1/3, that is the square root of 8 raised to 1/3, the result is 8 raised to 1/6. Then copy the e, multiply this exponent to that exponent to arrive at I pi over 12 plus 2/3 pi k. Now, simplifying this 8 raised to 1/6, we arrive at square root of 2, and we copy the rest. So again, this value for c depends on what is the value of k. So if k equals 0, then we have this solution, square root of 2 e raised to I times pi over 12. And this pi over 12 is around 15 degrees. If k is 1, we have the solution, square root of 2 e raised to I times 9 pi over 12. And that is about 135 degrees. And for k equals 2, that is square root of 2 e raised to I times 17 pi over 12. And that is about 255 degrees. So what's the interpretation of this? Originally, our angle was 45 degrees. But when you find a complex number such that you need to raise it to the third power in order to get 45 degrees, the resulting angle is only 1/3 of the original 45 degrees. Whereas for the magnitude, originally, the magnitude of the vector was square root of 8, but now we have here a magnitude of square root of 2. But if you raise square root of 2 to the third, that would go back to square root of 8. And there are so many possible answers here, and you can arrive at those answers by rotating around this circle. And so for our final answer now, this is our general solution to this equation, z cubed equals 2 plus 2i, and our solution is c sub k is equal to the square root of 2 e raised to I times pi over 12 plus 2/3 pi k, where k is equal to 0, 1, 2, 3, and so on. Bye for now.